Hello calculus, and welcome back for another week of videos. I hope you are safe and well and at home. This video we're going to start off with the derivative of the sine and cosine functions, and I'm going to prove for you how we get this. But just so you know, from your textbook we have theorem 3.8, and that gives us these two facts. That if I take the derivative, d by dx, of sine of x, the derivative of sine is cosine of x, and the derivative of cosine of x equals negative sine of x. Now, if you've taken a class with me in person before, you know I'm not big on memorization. These, I think, are worth memorizing. So I'll do what I did for my previous class, and I'm going to tell you, these belong in your heart. These are worth knowing by heart. You should know them because you love math. And even if you don't love math, you should know them because you love being able to do complicated derivatives quickly. So these are worth writing in your heart. I say writing in your heart instead of memorizing because a lot of us have negative feelings about memorizing stuff. These are going to be so useful that they're worth just knowing. So I would say keep these in mind. And I'm going to go ahead and do the proof that's outlined in your textbook. So the proof for both of these rules are very similar. So I'm just going to do one, and then if you're interested in the other, I think you should try to follow my steps and see if you could figure it out. So I'm going to prove that the derivative of sine of x equals the cosine of x. And the proof of the other fact is basically the same as this one. So we're going to need, that was a great way to spell need. Whoo, that quarantine's getting to her. We're going to need some facts for this proof. So the first thing that we're going to need to do is remember something from our trig. If you are like me, that is difficult, but it's okay. We have here a formula that tells us if I have the sine of the sum of two angles, x plus h, then that is equivalent to this statement. Sine of x times the cosine of h plus the cosine of x times the sine of h. This is a fact from pre-calculus, from trigonometry, so you can look it up if you want a proof of this or if you need more information about it. We're also going to need to remember a couple of limits that we did way back at the beginning of the course. So we need to remember these two limits. Both of these facts are going to come up in our proof, and we're going to need to be able to use them. So we're going to need to remember that the limit as h approaches 0 of sine h over h is equal to 1. That's the very first limit I had you guys do. Aw, memories. And we're going to need to remember that the limit as h goes to 0 of cosine of h subtract 1 divided by h is equal to 0. So we're going to need to remember these two limits. And the limit definition, I said two facts, but I'm going to go ahead and throw in a third, that f prime of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So this last one is just the definition of the limit. When I have a function f of x, f prime of x is given this way. And we are ready to go. So this is a fun, straightforward proof. I'm going to start off by applying the definition. So I'm going to say, look, we have the derivative with respect to x of our function sine of x. And if I apply that third definition, that third fact that we used right here, if I take this and I apply it in this situation, I'm going to get the limit as h goes to 0 of the sine of x plus h minus sine of x all over h. That's just me applying my third fact there. And now you might see, look, I have the sine of x plus h here. That was our first fact. I wanted you to remember that the sine of x plus h is equivalent to this statement here. So what we're going to do is going to replace this with that. That's going to be our next step in this proof. Okay, so now we have that the derivative of the sine of x is equal to the limit as h approaches 0. I'm replacing the sine of x plus h with sine x cosine h minus cosine x sine h minus sine x, all divided by h. And what I'm hoping you see here is that we have some common factors. I don't want that to be red. We used red already. I have sine of x here, and I have a sine of x here. So all I'm going to do is rearrange my terms and bring this one forward so that I can factor. So I have the limit as h approaches 0 of sine of x cosine of h minus sine of x minus cosine of x sine of h. And so again, and then that's all over h. And so now I have my sine x and my sine x here. And I'm going to factor that sine x out. The limit as h approaches 0. I'm factoring out my sine of x, and what remains is cosine of h minus 1. And then, oh, I think I messed up a sign here. Guys, I totally messed up a sign. Look at this. Sine of x plus h. I'm supposed to have an addition sign here in the middle. Do you see that? Addition. Let's scroll down and see what I did. Subtraction. Why did I do that? I don't know, but let's go ahead and fix it. Addition. Addition. Glad I caught that. All right, that would have made us get to the very end of the proof and have everything totally wrong. I only was able to catch that mistake because I know that my next step relies on that being addition, and that's a pretty important one. Okay, so here we are. All I did was I took out this factor of sine x, and now I'm going to use a limit property. Some of you kept saying, when are we going to use these limit laws? And I kept saying, all the time, all the time, all the time. Here I am fulfilling on that promise. So what I'm going to do first, before I do that limit law, is I'm going to use a property of fractions. So we have the limit as h approaches 0 of sine x times cosine of h minus 1 all over h plus cosine x sine h all over h. So what I did was I recognized that I have a common denominator of h, and that I can add these two pieces of my numerator together, and that I can then separate them out like this here. Now I'm ready to use a property of limits, which says that when I have an addition sign here, that's what I was remembering, that if I take the limit of this entire thing, it's the same as if I take the limit of this, and then I take the limit of this, and then I add them together. So I'm going to use that limit property to separate this into two distinct limits. So my first limit is the limit as h approaches 0 of sine x times cosine of h minus 1 all over h, plus the limit as h approaches 0 of the cosine of x times the sine of h all over h. Now I'm going to do another fancy thing with fractions here, which is that I'm going to factor out the sine of x and the cosine of x here. And that's going to look like this. I have the limit as h approaches 0 of the sine of x times the cosine of h minus 1 over h. Let's use parentheses. I feel like that looks a little clearer. Plus the limit as h goes to 0 of cosine x, and then in here times sine of h over h. So I can justify this by realizing that sine of x is the same as sine of x over 1, and then if I did multiply this back in, what would happen is I would say 1 times h and sine x times this thing on top, and then I'd get back to my original statement. All right, and maybe you guys are starting to see the method to my madness here, because this here and this here are among some of the two facts that I laid out at the beginning of this video. So let me go back and look at those facts and remind you. I wanted us to remember these two limits. Here's the sine of h over h, and here's the cosine of h minus 1 over h. So I wanted you to remember that sine of h over h, if I take that limit as h goes to 0, my answer is 1. And cosine of h minus 1 over h, if I take that limit as h goes to 0, my answer is 0. So that's going to help us in this next step here. Okay. So now I'm going to use another property of limits that says that I actually know that the sine of x by itself right here has nothing to do with h, right? There's no way that that's going to change. So with respect to this limit as h goes to 0, the limit of sine of x is just going to be sine of x. And then this limit right here, we just know from our facts, that's going to become 0 as I take the limit as h approaches 0. So this becomes the limit of sine of x, which stays the same because there's no h to affect it, multiplied by 0. Similarly here, cosine of x doesn't have anything to do with h. So when I take the limit as h approaches 0 of cosine x, my answer will just be cosine x. And this that I highlighted in blue is a known limit of 1. And now all I have to do is some algebraic simplification. Sine of x times 0 is 0. And cosine of x times 1 is cosine of x. So I have 0 plus the cosine of x, which is just the cosine of x. So all that work goes in to show us that when I take the derivative of sine x, I get cosine of x. And that is your proof of this fact. Yay! Worth knowing. If you're interested in the proof of the other fact that we have here, if you're interested in this, in why the derivative of cosine x is negative sine x, you would use almost the exact same steps to prove it. It's very, very similar. So see if you could figure that out. You know, all we did here was use these facts. First, I applied the definition of a limit. Then I used a formula for the sum of angles. I did some factoring. I used a limit property. I did some more factoring. I used another limit property.